Humans count with 10 digits because we have 10 fingers, but computers operate on physical electrical circuits that can only exist in one of two states. The switch is either off, which we call 0, or it is on, which we call 1. This table compares our decimal system with the bases computers use to process information. While decimal gives 10 options per digit, binary gives only 0 and 1. Systems like octal and hexadecimal expand this, using 8 or 16 digits. Translating decimal data into binary logic is the first step in understanding how all computer memory actually stores information. Converting a decimal number into binary requires a process called repeated division. You divide your target number by 2 and isolate the remainder at each step. For the number 42, we divide by 2 to get 21 with a remainder of 0. We divide that result by 2 again to get 10 with a remainder of 1. By repeating this until we hit 0, we extract a sequence of 1s and 0s. We see the same process with the number 50. We divide until we reach 0, isolating each remainder. To get the correct binary string, read those remainders from the bottom to the top. 50 becomes 110010. This manual math maps directly to a C++ program. We use a while loop that runs as long as our decimal number is greater than 0. Inside the loop, we calculate the remainder using the modulo operator, and then divide the number by 2 to prepare for the next iteration. To construct the final number in our code, we use a power variable. By multiplying our current answer by 10 and adding the new remainder, we are shifting each new bit into the correct tens, hundreds, or thousands place. The way you solve the problem on paper provides the exact structure needed for the code loop. Converting binary back to decimal works in the opposite direction. We read the string from right to left, assigning each digit a value based on powers of 2. If we map the binary string 101010 to this chart, we see each position's value. We have a 1 in the 32 column, the 8 column, and the 2 column. Adding those together brings us back to our original decimal 42. The C++ code for this conversion follows a similar loop, but with a key difference. Instead of shifting digits visually, we multiply the power by 2 in each step to calculate the actual mathematical weight of each bit. Your conversion goal determines the logic. You are either building a visual string of bits or calculating a single numerical sum. You can speed up these conversions by skipping the division and using a simple subtraction chart. To convert 25, we find the largest power of 2 that fits inside it, 16. We subtract 16, leaving 9, and put a 1 in that column. Since 8 fits into 9, we put a 1 there, leaving 1. 4 and 2 are too large, so they get zeros, and our final one fits in the last column. This method highlights a specific property. Because 2 to the power of 0 is the only odd value in the set, any odd decimal number must result in a binary string ending in a 1. Try this with decimal 37. By combining 32, 4, and 1, we get 100101. The final bit is a 1, confirming the number is odd. Recognizing these bit patterns allow you to determine basic data traits, like whether a number is even or odd, without running complex calculations. Binary addition follows the same logic as decimal addition, but with only 2 digits available. When you add 1 and 1, the result is 0, and you carry a 1 over to the next column. Let's add 5 and 3 in binary. In the right column, 1 plus 1 gives us 0, and we carry that 1. This carry ripples through the next 2 columns, resulting in 1000, the binary form of 8. Carrying bits follows the same principle as the math you already know. You are simply working within a 2-digit limit. Understanding these base-level conversions provides the necessary context for bitwise operators, which allow you to manipulate these 1s and 0s directly to optimize your code. We have covered the 4 pillars of the binary system: the rules of base 2 logic, the code for decimal to binary conversion, the math for reversing that process, and the rules for carrying bits during addition. Save this summary for your notes. It serves as a reference for the rules of binary conversion and addition as you move toward more advanced bitwise programming.